Good morning. How's everyone feeling? All right. A couple of things to talk about here at the start. There may be some new faces in the audience because the school has opened up 2 additional registration options for this particular class. So previously there was only lab on Tuesday and Wednesday, but now they have added a Monday lab. So there are now a total of 2 extra course registration slots because now it's 2 lectures and 3 labs, so 6 total, 3 times 2. So if you weren't here on Monday and Wednesday, welcome. I'm Professor Hoffbauer, and it's nice to have you all, and I look forward to working with you. Some things, if you are new to the course, I need to make sure that you are all in the course Brightspace page because I always have issues getting everyone added there. If you are unable to log into Brightspace and see Hoffbauer, the physics of how things work, spring 24, I need you to email me to make sure that I get you added. Now, if some people are already on there, if you are there already, then you will be able to open the course and within the Introductions and Resources tab, view things like the formula sheet, the notes I've presented so far, and the course syllabus, which has all the pertinent details about the class, including a link to the YouTube channel where I post all of the recordings of all of my lectures. I record everything, so if you ever missed something or need to watch it again, you can follow that link to go to the place where those are all stored. So if you weren't in the course yet on Monday or Wednesday, you can watch those to make sure that you didn't miss anything. Although on Monday and Wednesday, all we really did was talk about the course syllabus and then the scientific method. But you should still check those out if you weren't present at the time. Now, this now applies to everybody, not just new students. Because there is now a Monday lab, I have to consider the fact that next Monday is MLK Day. That's the 15th? Monday the 15th? And I have a policy of making sure that one lab section doesn't get ahead or behind of the others. I want every lab within 1 week to be the same activity. And that means that since Monday doesn't exist next week, there's no lab at all next week. So we aren't actually starting labs until the 3rd week of the semester, as it happens. There will not be a lab at all next week because there is no 4 classes on Monday. So official announcement, no lecture Monday, no lab at all next week. Cool?
Yep.
All right. I think that was the main announcements. How y'all feeling? Does anyone have any questions before we get started today? Okay. One last thing. Because of the new course sections that have opened up, if you were already registered for either the Tuesday or Wednesday lab, and the Monday lab works for you, I would please ask and encourage students to transfer your course registration from Tuesday or Wednesday to the Monday so that we can make sure that people who can only do Tuesday or Wednesday and are on the wait lists can get into the class if they can't do the Monday one. So if you can move your course registration around, I would politely ask you to consider doing so that we can try to make sure the course is distributed as possible among the whole week and so that people who can only do Tuesday and Wednesday are able to get those slots. Sound fair? All right. Once again, any questions, issues, etc. before moving on today?
Is that Monday lab at the same time?
Yes. Lab as always starts at 1:30 and will be done at the absolute latest by 4:30. It's just the time that the school puts the labs at. All right. Now, let's see. Our main topic for today is going to be looking at the units of measure and unit conversions that we're going to be using throughout the semester. On Wednesday, we talked about scientific method and how we like data, we love data, and since data is numbers, we have to talk about how we measure those things and the things that we do with those numbers once we have them. Bless you. We're going to be taking a lot of measurements between lecture and lab, and as a result we need to be familiar with the units that we will commonly be using. Physics likes to use the metric system. Common metric units are currently visible on screen as a bit of a preview. Metric system means that we have to convert non-metric units into metric units, and we also have to be familiar with what those common units are and also the metric prefixes. So today is largely going to be a mixture of looking at those units, familiarizing ourselves with the things we have to commonly do with them, and then eventually moving on to algebra practice. Some of the first couple of units we're going to be using are currently on screen. We're going to be adding to this list as the semester goes on. Whenever I give you a new unit of measure, I'll always make sure you know what it's called, what it's shortened to, where you'll commonly use it, what other units are commonly used to measure that thing. I'll make sure you have everything you need to know about it. For instance, first couple things we usually measure in physics, we've got displacement measured in meters. We like meters as opposed to feet or inches or miles. For velocity, meters per second as opposed to miles per hour. Acceleration, meters per second squared. There's not really a commonly used unit for acceleration in American, at least not in my experience. For force, we like newtons, named after Isaac Newton himself. In American, we tend to use pounds, but wherever you would use pounds, we will use newtons instead. Now, I'll always make sure that you have any conversions that you need. You never have to memorize any of them because, frankly, I'm awful at memorizing them half the time. But just for scale, just to kind of work on your sense of scale for the semester, I'll list some of these common conversions over here just to help you get used to them. 1 meter is about 3.3 feet, slightly longer than a yard, and 4.4 newtons is the equivalent of 1 pound. So you take what you weigh in pounds, multiply it by 4.4, and you get your weight in newtons. Again, for scale, I, average adult human male, weigh about 1,000 newtons. For mass, we like kilogram, and for time, we like seconds. This is kind of a weird exception to one of the usual rules in this class. Typically, we use base units with no prefixes. Kilograms is the weird exception. Physics likes kilograms instead of normal base grams for mass. We'll get into that a little bit more later. Mass will come up in a week or so. But just to kind of briefly talk about it because it's in my head at the moment. Base grams tend to be used more by chemists and biologists because if you take in a chem lab, you're familiar with working with a teeny tiny pile of dust that you add to a teeny tiny amount of liquid. Does that sound right? So chemists work in grams because they tend to work with small amounts of things. Physicists tend to work with things the size of people and cars and meteors. So those things have bigger masses. We use kilograms to make the numbers smaller. That's, as best as I can tell, the only reason. But again, we'll get into the habit of using kilograms as we start doing mass calculations. Again, any new unit, I'll make sure you have all the pertinent information about it. But in addition to units, we also have to be able to use the metric prefixes. Has anyone not used these before? All right, just checking. The ones outlined in red are the most common ones, the ones summarized in that age-old mnemonic, King Henry died by drinking chocolate milk. The line is base, which is just B, by in the mnemonic. But I like to write a line just because it represents the basic unit with no prefix. And on this chart in the notes, the blue line here is the base unmodified unit. And then for every prefix above that line, you make the unit bigger. For every prefix below that line, you make the unit smaller. 1 decameter is 10 times bigger than a normal meter. 1 hectometer is 100 times bigger than a meter. And 1 kilometer is 1,000 times bigger than a meter. You never really use hecto or deca, though. So You don't have to memorize these, but, I mean, you should be familiar with K through M regardless. Yes, sir.
How many, kilograms is equivalent to a pound?
Ooh. Okay. Well, okay, let me answer your question first. I want to give you the answer to your question before I get off topic. Kilograms per pound. 1 pound is equivalent to 0.454 kilograms on planet Earth. Now, this is now a nitpick. I'm rambling a little bit at this point. Pounds is a unit of force, and kilograms is a unit of mass. And so technically, one shouldn't convert straight from one to the other because they measure different things. This is a nitpick. I know in, frankly, all of Europe, they use grams as a unit of weight, and that bugs me. The issue there is mass stays constant if you go to the moon, but weight doesn't. So technically, they don't measure the same thing. Now, they are used that way on Earth. It's not a problem as long as you stay on Earth, but that's it's a small grievance I have with British English. Does that answer the question? Okay. Sorry for the tangent. But you know what, for completeness sake, I'll put an asterisk by it, but I will mention 1 pound. Just for your sense of scale. Now that's only true on planet Earth, that's my nitpick. Also, my ones look funny because I want to make it clear that I'm writing a 1 instead of an L. Back to metric prefixes. Below the line, things get smaller. Deci is 10 times smaller. Centi is 100 times smaller. Milli is 1,000 times smaller. And then there's even more extreme prefixes outside of the red box. We won't use them often, but if they come up, I'll make sure you are told what the actual conversion factor is. I might use mega or giga sometimes just to emphasize how big something is. Meanwhile, in terms of smaller, micro might come up once in a blue moon, especially when we get into the end of the semester and talk about electricity, because we tend to use very small amounts of electricity to avoid hurting ourselves. But for scale, I believe attometers is about the time you get to the size of molecules. At the very least, 1 attosecond is, I think, the smallest amount of time we can measure, just for, again, context. Now, again, the ones in the box are the ones you have to operate with most. Those are the ones summarized by King Henry died by drinking chocolate milk. And so those are the ones that we will now briefly practice. So, we got 5 conversions on the board. And I would like to give you guys a brief moment to convert them from one thing into the second thing. Give you guys a couple seconds, minutes to work on that on your own, and then we'll just go over it quickly together. All right. How many kilometers are in 10 meters? 0.01, very good. Now, I've been doing this enough to just know that if I'm going from base to kilo, I would divide by 1,000, because if the unit gets bigger, the number gets smaller. But some students like to use the visual conversion method, so I'll just show that real quick. 10 begins with the decimal point there, and if you do want to visually use this to drag your decimal place around, to go from base to kilo, you need to drag your decimal point 3 places to the left, which is the same as dividing by 1,000. 1, 2, 3, decimal point there. So yes, 10 meters is 0.01 kilograms. As a small note, I tend to put a 0 in front of my decimal points. I find that it makes the decimal point more visible. So if I was just doing this on my own, that is how I would leave my answer. I just find that it makes it, I feel like it makes the decimal point a little more obvious. All right, kilograms per 100 centigrams.
0.001.
Very good. That would be dividing by 10,000, or visually speaking, 5 places to the left. So starting at 100, 1, 2, 3, 4, 5, 0.001 kilograms. All right, now, kiloliter, 1,000 kiloliters to milliliters.
Is it 10,000?
It is not 10,000. That is because there is 1,000 liters in a kiloliter, so you multiply by 1,000 to get from kilo to base, but then there's 1,000 milliliters per liter. So to go from base to milli, you multiply by 1,000 again. To do this visually, starting at kilo going to milli, you have to drag a decimal point 6 spaces to the right. Thank you.
That's
It's actually a billion, because you already had 3 zeros, and now you're adding on 6 more. So, just for context, 1,000 kiloliters, liters measures volume, so you might measure like volume of water. 1,000 kiloliters is a lot of water. That would be, yeah, 1,000, actually, I guess 500 2 liters of soda. And converting that into milliliters just makes the number huge.
so that's milliliters?
Yep, ml is milliliters. Lowercase m on the front is milli.
Okay. What if it was if it's just a regular liter, it'd just be L?
Yeah, so regular L is liter, KL is kiloliter, ML is milliliter. Now, if it's an M by itself, that would be base meter. It's only milli if it's out front of another unit. All right, a couple more. How many meters are into 25 kilometers?
25,000.
25,000. And last up, grams per 0.25 kilograms.
250.
250, very good. This conversion out of all of them is akin to one you'll have to do pretty commonly, except we like kilograms over grams. Every formula I give you is going to assume kilograms instead of grams. So you're going to have to do this one backwards pretty frequently. So actually, I guess more similar to this one. But how do these feel? All right. Now, these are not the only types of conversions you will have to do. Because not every unit is a metric unit that our formulas are designed to utilize. And so, not uncommonly, you'll have to take a non-metric unit and convert it into a different metric unit. So we need to practice that too. Namely, I want to do these to make sure that you are familiar with the method that I use when I'm writing out my work for unit conversions, since I'm the guy that's going to be writing stuff on the board, and I want to make sure that my notes make sense to you. So I have a specific tactic I use, and I want to make sure you're familiar with it before I start doing too much math all at once. So let's start out with a basic example. How many seconds are in one day? You probably figured out similar things like that before. Like how many seconds are in a minute? 60. It's not a trick, I promise. 1 minute, 60 seconds. How many seconds are in an hour? Minutes, excuse me, are in an hour. Again, not a trick. Thank you. Hours in a day. All right. Oops. Started writing in reverse order. So you guys know this, and you could choose any method you want to turn hours into seconds. You'd probably just end up multiplying 24 by 60 by 60, which is fine. I just want to make sure that you've seen the way that I do conversions. So I'm just going to use this as a sample to demonstrate what I put on the board. When I'm doing a conversion on the board, I always first write down the number that I start with, the number I'm given, along with its unit. In this case, I'm writing 1 day, and my goal is to turn that 1 day into the equivalent number of seconds. And the way that I do that is, I take these conversion factors and I use them as fractions to modify the starting number. Now for this to work, there's a couple math properties I want to review briefly. These are equivalencies. This is 1 minute is equal to 60 seconds. That means that by definition, these are the same thing. They're just different ways of writing the same thing. Does that make sense? Now, I can treat these as full equations. I could treat this, if I wanted to, as 1 times minutes equals 60 times seconds. I can treat minutes and seconds as if they're part of an equation. And what I'm going to do with that is, I am going to take this equivalency, 1 minute equals 60 seconds, and I am going to divide both sides of this by 60 seconds. I'm trying to eliminate 60 seconds from one side and send it to the other algebra style. So I'm going to write out what that looks like. Whatever you do to one side, you have to do to both. We'll be reviewing that too. But I'm dividing both sides by 60 seconds. I'm treating this as part of an algebraic equation. So, this is the step that I've written out. Now, on the right, I now have 60 seconds over 60 seconds. And if you divide anything by itself, what do you get? 1. You get 1. 1 over 1 is 1, 2 over 2 is 1, etc., etc. Anything divided by itself is 1. So this entire right side, I can choose to simplify to be just the number 1. So basically, I've just taken something that was in the numerator on the right side and sent it to the denominator of the left side. Again, algebra, PEMDAS, send thing from one side to the other. We're going to be doing that a lot this semester. And in doing so, I've turned the entire right side into just a number 1 and the left side into a fraction. 1 minute divided by 60 seconds. Now this is still an equivalency. This fraction is equal to 1. And what happens if I multiply anything by 1? Same thing. Multiplying by 1 does not change a value at all. 5 times 1 is 1. I said that wrong. 5 times 1 is 5. 6 times 1 is 6, etc. That means that using this tactic, you can take any equivalency and transform it into a fraction equal to 1. And since that fraction is equal to 1, I can multiply anything in the universe by this fraction, and that does not change its value because that fraction is equivalent to 1. That make sense? And I'm going through all of this just to explain the conversion method I use. So what I'm going to do is, I actually grabbed the wrong statement here. I should have started with this one instead. I'm going to take 1 day equals 24 hours and turn it into a fraction that equals 1. And I'm going to place it, take that fraction and multiply it by 1 day in such a way that I don't change the amount of time, but I do change the unit attached. So 1 day equals 24 hours. If I do the same thing I did over here, I can turn this into a fraction that says 24 hours over 1 day. So I did the same thing, I just turned the equivalency into a fraction that still equals 1. I'm multiplying 1 by 1 day, but I've oriented the fraction in such a way that we now have days times hours over days. Because the denominator within the fraction is still underneath the number you're multiplying by the fraction. And that means that the unit of days cancels out. Does that make sense? Does that not make sense? Better question to ask. The way that I wrote this, days are gone. Now I'm just left with units of hours. So in short, if you multiply 1 day by 24 hours per day, days cancels out, you're left with 1 times 24 hours. So really we didn't technically learn anything here. We still already knew that 1 day is 24 hours, but you can add links onto this chain. And that's, if you keep adding pieces onto it, it starts to look something like railroad tracks or fence posts, and that's why some people call this the railroad method or the fence post method. Because I can keep going and I can keep turning our new unit into something else. For example, I can turn hours into minutes and then minutes into seconds. You just have to make sure that you orient your fraction such that the old unit gets canceled out and replaced with the new unit that you actually want. So now if I want to turn hours into minutes, multiply by the equivalency fraction with hours down here and minutes up here. So 1 times 24 times 60 converts days into minutes. And then same thing, adding another link on for minutes to seconds. 1 times 24 times 60 is the seconds per day. All that preamble just to get to what I want to put in my calculator to make sure I get seconds per day. As long as you do it right, as long as you input it correctly, you can now just lump this whole thing into your calculator in one line, as long as you're using, a scientific calculator like I told you to have. Doesn't have to be the same as mine, as long as it can handle something like this. So 1, open parentheses, 24 over 1, close parentheses, 60 over 1, close parentheses, 60 over 1, close parentheses. Which is the same as 1 times 24 times 60 times 60. But sometimes the fractions won't have a 1 in them, so you need to be familiar with doing this in case it's not just always a 1 on the denominator. Bless you. And if you input that into your calculator correctly, it should spit out, if memory serves, 86,400 seconds. The number of seconds in 1 day. How's that feel? As something that I do on the board, do you think it'll make sense? That's my goal here. make sure that this is just how I do things out of habit. I want to make sure that doesn't mess people up when I put it on the board. Okay, no complaints. You're allowed to complain. I want to know if you have any. Feedback is appreciated. All right. So, got a couple more examples on the board that I want to run through. Next one, we'll just practice the same thing, but with a slightly more complicated or slightly more involved set of conversions. We are going to turn 80 miles per hour into meters per second, because in American we like miles per hour, but in physics we need meters per second instead. I'm just going to do the same basic technique, except any complaints if I erase this?
Can you keep like 2 seconds?
Yeah. While I'm waiting, I'll point out that I have listed within the question the equivalency between meters and miles. Again, you will never need to memorize a conversion in this class. I'll make sure you always have them. Either if you're doing homework out of the book, they'll be in the book. If you're doing homework from the copy that I post online, I'll make sure it's written there. And when you are doing tests and labs, I will make sure that the conversions you need are in the document or on the course formula sheet. We good now? So you don't have to memorize conversions, just like how you don't have to memorize any formulas. You have a formula sheet. You can even write this on your formula sheet, if it's not already there. So, I always write out the thing we start with. That's going to be 80 miles per hour in this case. But instead of mph, I'm going to put that into fraction form. Miles divided by hours. And we have to eventually transform miles into meters and hours into seconds. Sometimes I put the unit I'm after on the far side just to make sure that I'm tracking things correctly. And again, the way that I like to do it, I'm just going to multiply by a bunch of fractions to cancel out what I don't want and replace it with what I do. So let's turn miles into meters. There is 1,609.34 meters in 1 mile. I can turn that into a fraction. I just need to make sure that the correct unit goes in the correct spot. So, where should I write the 1,609.34 meters in this fraction?
On top.
On top, very good, because I want meters on top in the final answer. And the big number attached to the meters has to go with it. That means that the other part, the 1 mile, has to go on the bottom. And that, I want to make it clear, MI is mile, M is meter. I appreciate that might be a little weird. Mile isn't a standard metric unit. But note, mile here divided by mile there, miles cancels out and leaves meters behind, which is what we wanted. Now we have to turn hours into seconds. Now I've been doing this for so long that I do happen to have memorized the number of seconds in 1 hour. 1 hour is equal to 3,600 seconds, which is just 60 times 60. You could do it this way. You could do 2 links doing hours to minutes and then minutes to seconds. Either method is fine. This is just stuck in my head after doing this for 15 years. Whichever version you prefer, either adding in the step for both or jumping straight from hours to seconds. We do have to orient it like this because hours is initially on the bottom, so to cancel it out, we have to actually put it on the top of our multiplication fraction, and that leaves seconds behind on the bottom right where we want it. So now, this would be what we put into our calculator to get from 80 miles per hour to meters per second. I'll write out, again, a representation of what buttons you should press. pop that in your calculator and hit go. You should get 35 and a half or so, if memory serves.
35.7632.
Thank you. So if you're going from mph to meters per second, it's usually a little less than half, about 40%.
So that's 35.76 meters or something?
Meters every single second. So if you're going this quick on the interstate, we're zipping literally about 36 entire meters in a single second. Yes?
So the top half, do we have to do that? Or
Sorry.
can we just skip down to the 80 with, times 1 with the 3,600?
Oh, you can absolutely jump straight to here if you want to. I wrote this to try to represent how it usually looks in your calculator, but if you like just skipping straight to here, you absolutely can. This is just what I usually write on my work to make, so that I make sure for my own benefit everything's where I want it before I put it into my calculator. You do not have to use the same method I do. At this point in your math and science work, you've probably converted units before, you've probably got a preferred method. You don't have to do it my way. I just want to make sure that what I put on the board makes sense. Does that answer the question? How's that one feel? All right. I got one more sample one up here real quick that I want to do, primarily because there's two additional catches in this one that I want to make sure you're familiar with. So, I'll read this last one out loud. A rectangular building lot measures 1.00 times 10 to the second feet by 1.50 times 10 to the second feet. Determine the area of this lot in meters, square meters, or otherwise known as meters squared. Assume 1 meter equals 3.3 feet. So the first catch that I want to review, these sides are listed in scientific notation as opposed to as a normal number. So how many feet written normally is 1.00 times 10 to the second? 100, very good. And what about 1.50 times 10 to the second?
150.
Very good. So, if I haven't said it out loud yet, we will use scientific notation in here. That's just referring to the tactic of writing your numbers like this. Just a trick to make sure that sometimes you don't have to write out all the zeros if your number's really, really big or really, really small. And we will be dealing with really, really big numbers because the mass of the moon might come up. And we will be dealing with really, really small numbers because we might occasionally have to deal with the mass of an atom. So, scientific notation is something we're going to have to deal with. Make sure that when you see this, it makes sense. Also, your calculator is probably going to spit out numbers in scientific notation occasionally as well. This is our building lot in feet by feet. How do you find the area of a rectangle? Length times width, so 100 times 150, that's going to give us 15,000. What would the units be if we did this? Feet squared, because we multiplied feet times feet. So that is the area of the lot. It's just not the unit we were asked for. We want this in meters squared, not feet squared. So we have to convert. Now I did mention that 1 meter is 3.3 feet, so we can use that to turn the feet into meters. I would want to make sure that the feet part of this is on the bottom of my fraction so that it cancels out with the feet in the numerator of the basic unit, leaving meters behind in the numerator so that we get the unit we want. And then, are we good to go from here? No, what's the catch?
Bottom feet isn't square.
Exactly. Feet squared, bless you, is feet times feet. If you divide feet squared by feet, you don't cancel out the feet and leave a squared behind, because feet squared is feet times feet. If you take feet times feet and divide by feet, you still have feet. Yes, this is weird to say out loud. But, to try to summarize, if this is all we do, we don't cancel out feet squared, we only cancel out the square. So if you only multiply by this ratio once, your final answer would actually be in units of feet times meters, because we left the foot behind. And feet meters isn't a thing. That would make Americans and Canadians upset. So if you are ever converting a squared unit, or possibly even a cubed unit, you need to add a step onto your link for every part of the square of the cube. We would tack on one more 1 meter over 3.3 feet to make sure that we got both feet, and now we're actually left with meters times meters, which is meters squared, which is what we want. So this one's in the notes to 1, make sure you can do scientific notation, and 2, make sure you catch this whenever you have to convert a squared or cubed unit, which will happen on occasion. I did mention earlier, a pretty common unit that we will use has a squared in it. Unit for acceleration is meters per second squared. So this will come up. It's not super often, but it's often enough that you need to know how to do it. Get that final answer before I move on.
So we just added another one that cancels the feet out.
Yep, we multiply by the fraction again.
You could simplify that though by just putting like a squared behind the first set of the fraction though, right?
You absolutely could. So, yeah, I'm running out of board space. I'm gonna move to the other side. You could square that fraction. Like the two ways that I would say put that in your calculator would look like 15,000 times 1 over 3.3 times 1 over 3.3. Or you could do this, which is what you were hinting at. Now, if you do this and say, like, you were trying to work it out manually, note that if you square a fraction, you have to square every part of it. So this would technically be 1 squared over 3.3 squared. Now 1 squared is 1, so that doesn't mean anything here, but if it wasn't a 1, you'd have to note that. You'd square every single thing that this square is attached to. But yes, you are absolutely right. And that should tell you that u squared 3.3. 1 foot squared is about 10.89 meters squared. No, did I get that backwards? 1 meter squared is 10.98 feet squared. Sorry. Anyway, final answer. Either way you input that should be, please correct me if I am misspeaking, 1,377.4-ish meters squared. Bless you.
Thank you.
Now, somewhat off topic. I'm pretty bad about grading about sig figs. I don't usually require them, but I do get loads of students asking me, at the very least, where should I round off my answers? If I'm not grading about sig figs, which I'm not unless I tell you that a question involves sig figs, my golden rule is usually cut it off at the hundredths place. But just for the sake of completeness in this particular example, conversions are usually given to have infinite precision, so we base the precision of our answer on our starting numbers. which each have 3 sig figs apiece. And since all of this was multiplication, the first 3 digits of our answer are significant. Now, I don't grade to that, but I wanted to mention it just in case. I get questions about it sometimes. Questions, concerns? Anything on your minds? Physics is hard, and that's okay. That's why the homework isn't graded. You're meant to make your mistakes on that and not on the test. Now, on Wednesday, because I won't see you on Monday, we're going to continue talking about units in the sense that I want to make sure you know what a vector is. And then we're going to begin chapter 2, where we start looking at the first things that we're going to measure and calculate, which is forces and motion. Does it feel good for right now? All right. Let me know if you have any questions about anything at all, including and especially course registration stuff over the weekend. I will see you Wednesday. There is no lab next week at all and no lecture on Monday. And